Here is a portal frame, a plastic collapse mechanism. We're going to see this in the next few minutes. We are assuming here all sections are fully restrained and all members are class 1, so that the full plastic moment capacity can be attained. When the critical plastic collapse mechanism is formed, what would be the minimum required load W in terms of MP to cause plastic collapse mechanism? And then we compare this with all the other mechanisms that we're going to see. Here we will see that the two loads are applied. We are assuming the same W for vertical and W for lateral load. Of course, there is going to be one due to vertical load, a sway mechanism due to lateral load, so beam and a sway. We'll take this load separately and see what is going to happen on our structure. But bear in mind, when we come to the beam mechanism, these I sections, if we check that it is class 1 cross section, of course D over thickness of wave or B over thickness of flange, and we check that class 1 sections and we try to use it for the beam. We also need to consider these class 1 sections need to develop, need to have that restrained by flanges or top slabs, so that it will not cause a rotation or move laterally and rotate and buckle in early stage before it reach that plastic MP stage or plastic collapse mechanism state. So we don't want it to fail before it reaches our intention design, because we design it assuming that it will not buckle, it would reach that plastic collapse mechanism. So for that we will see how we can avoid. I mean, the way it is rotating and not going through rotation is like this. Now you see, it is not going to pass through the shear center of the web, so the whole structure will not form that the plastic capacity. That means it will fail. So that's called lateral torsional buckling. We will see that in my next videos in depth. So of course, now assuming it will develop the plastic hinge on the beams and considering the vertical load only, there is 3 hinges that needs this collapse mechanism to happen. These joints, the middle one and the third one. If these 3 joints are reaching that plastic moment capacity, it will collapse. So it will cause that plastic hinge. Then again here, because the load has done work externally and internally, we just have to equate this. The external work done is W times distance traveled dV. Now the way to find dV is by using this rotation theta angle, which is tan theta is opposite over adjacent. So opposite is, if we call it dV over 3 meter, so tan theta is small theta, small rotation, so tan theta is equal to theta, so theta is equal to dV over 3 meters, so dV is 3 times tan theta. That is a vertical work done, so that is W3 theta. The internal work done is, because this load, when it lands into our beam when it deflects, it dissipates the energy. The energy travels into these joints and then it causes joint to rotate by theta. So that rotation is caused by MP applied due to the load W. So internally it rotates, so internally MP applied, so internal job is MP times theta for these rotations. Of course, the same applied to this joint. This member has rotated by theta here, similar to this theta here, and this member has rotated by theta, similar to this theta here, so 2 theta. this one is 1 theta. Of course this one has rotated as well, so MP times this rotation theta is the internal work done. So there is 4 MP caused 4 theta rotations. If we equate that, so external work done is W times D V, which is W3 theta. Internal work done is MP4 theta. So W3 theta is equal to MP4 theta. We find that the W we need is 4 times the MP divided by 3, which is 1.33 times MP to cause that plastic collapse of the beam. That's just considering the beam mechanism. What if we consider for sway mechanism only taking lateral load W in this way? What would be the mechanism that would form? But bear in mind here is that now we are incorporating the whole members for collapse mechanism. So we've got the 2 columns and the beams, which means we cannot solve these equations with the sum of x vertical, horizontal load and vertical load, and then the moment equations to come up with the answer. So there's 6 unknown minus 3 equations is 3, so it is 3rd degree indeterminacy. Hence the number of hinges that we need to cause is R plus 1, which is 4. To form plastic collapse mechanism, we need to have 4 hinges, 1 over here, 1 over here, 1 over here, another 1 over here. Now from these 4 hinges, because W has done the job for the beam to deflect laterally, the distance traveled is dH. The rotation that it causes is theta for each plastic hinge joints. So we can work out the external work done, and we can work out the internal work done. Now it is, as you say, tan theta is, if we call this distance that travels dH, so tan theta is opposite over adjacent, so theta over 4. So tan theta is equal to theta because they are very small, so tans are equal because it is their sine over cosine. So we get theta times 4 is equal to dH. So the external work done will be W times 4 theta. Now the internal work done is this load has forced this joint to rotate, has forced that load to travel and this joint to resist, but internally it has twisted, it has moved the rotation, the joint, by the force of the load MP that has caused in this connection. So that rotation theta times MP is the work done that has done in these rotations in this joint. So the same apply to this joint. It has rotated by theta, and this joint has not rotated, but here these columns has rotated and this one has rotated. So they all have been rotated by the amount MP. So 4 MP times theta is the internal work done, and we get W, which is equal to MP. Now that's the amount of load that we need to form this way. When we come to the combined mechanism that we apply both loads, this is how it is going to be deflecting. We know that we're going to have 4 hinges that we need. They are here, 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 and here. Of course, there is no plastic hinge formed as this joint. We are assuming this joint stays 90 degree. if we lift this load, it would have gone back to its normal position because it has not reached to the plastic stage. But then again, because of these 4 plastic hinges, they have gone through plastic state, which means they are not going to get back to elastic. Once they have passed that limit, they will stay, the structure will stay deflected. But the work then has been done, the damage has been done into these 4 joints. The amount of work done internally is, of course, theta times mp. Here 2 theta times mp, here theta times mp, here is theta times mp, here is theta times mp. So externally we have dv, which is equal to 3 theta, dh, which is equal to 4 theta. So we got dv, which is w times dv, w times dh. So that is the external work done. We've got 7w theta. The internal work done is 6 theta times mp. When we equate that, we'll find the amount of load that we need is 0.86 times mp for the combined case. So we find that for the combined case, the minimum amount of load we need is in the combined case, because in the beam case is bigger than the sway and then combined. Now what if we select a member that can cause a collapse mechanism for combined case, which is for the minimum load? So if you take mp is equal to 35 kilonewton meter and then find w minimum, which is 6 mp over 7, 6 times 35 over 7, which is 30 kilonewton, and then try to see what will happen to the other collapse mechanism. Let's consider the beam collapse mechanism. In the beam collapse mechanism, we see that, of course, is the same collapse system. So external work done is equal to internal work done, which is w is 30 times 3 theta, which is equal to the 4 thetas rotation. This one is 2, that is theta theta. So when we equate that and we find mp 3w over 4, so 22.5 kilonewton meter. What does it mean? That it has not reached that plastic collapse mechanism. It has not formed the hinges. If we take off this load, the structure will get back to normal, which means we have not damaged the structure, which means if we don't have the lateral load, the beam alone can withstand this load. Let's get back to the sway mechanism. If we consider 30 kilonewton on the sway only, what happens is that the weight deflects, and then if we try to work out the external work done equating to internal work done, mp is 30 kilonewton meter, and the amount of mp that can carry is 35 kilonewton meter. And then again here, the sway alone will not cause that collapse mechanism for the structure, which means it can withstand the load. If we take off the load, the structure will get back to normal. Let's see the combined case. In the combined case, when we apply both vertical and horizontal loads, the external work done and the internal work done, when we equate the 30 times 4 theta plus 30 times 3 theta, which is 200 theta, internal work done mp times 6 theta, as we seen this earlier on. So mp 6 theta is 200 theta, mp is 35 kilonewton meter theta. So we got the same, our initially preferred member that can be caused to form the collapse mechanism, 35 kilonewton meter per second. So what does it mean? What does it mean in this structure? Now, what can we do if we have to keep the same portal structure with the same load, and then we've been assigned to make the analysis of existing structure? We have this kind of problems. What can we add as a member, external member, to keep this structure safe? Now there are, of course, a number of solutions. We can provide bracing, diagonal bracing, that can withstand this horizontal load, so that the structure can stay where it is, because we've seen that if we get rid of this load, the structure will stand. So providing the diagonal bracing is one solution. Of course, a number of ways. One, it can be a half bracing, one bracing like this, another bracing like this, considering that maybe you've got a door or a gate that you have to provide. Maybe you have to provide the windows or space, or if you've got extra space, that you can provide portals shape here, portal frame that can help to resist the side lateral load. So there are a number of solutions. Of course, in addition to that, we can upgrade the members, bigger size or bigger capacity, moment capacity structures we can provide into it, or then again maybe reduce the load, which is not actually, as a structural engineers, you want to keep the load. So maybe change the members, provide bracings, strengthen the joints, all sort of things that can be proposed for these structures. So this is how we can do a portal frame analysis. Thank you for watching. I'm trying to get 1,000 subscribers and do more of my time doing online teachings for structural and civil engineers. If you like what you see and you want to see more of this, please don't forget to like, share and subscribe. Thank you. Bye.